Hello, my name is Minkowski. I'm going to talk about cosmic redshift and how it's elegantly explained by Minkowski spacetime and general relativity. I have high expectations for this presentation. My expectations are that I'm going to be laughed at, ridiculed, humiliated, and told I should have done my homework. If these high expectations are not met, standard cosmology, in other words, space itself is expanding, is challenged. And so I call on you for some help on this. So why is cosmic redshift important? It's the key reason we believe that the universe is expanding. The further away we look, the faster the objects appear to be moving away from us. The basis for the scale factor AFT. We believe that the universe is expanding because there's no other satisfactory explanation for the redshift phenomenon. Light losing energy traveling through the vacuum of space hasn't yet been explained. But here's an explanation. It's consistent with conservation of energy, conservation of momentum, general relativity, other aspects of known and accepted physics. So what is new in this explanation? Well, nothing is new. It only incorporates two well-established principles. One, where and when can something be known? And two, gravity is an attraction between energy. Matter is largely a form of concentrated energy, the E equals mc squared thing. These points lead to an asymmetry in where energy could be known, and this creates an asymmetry in where gravity can have an effect. John Archibald Wheeler's quote is, matter tells space-time how to curve, space-time tells matter how to move, energy tells space-time how to curve, space-time tells energy how to move. Therefore, the location of energy matters. I have a two-atom, two-photon example. Here I've got two atoms on the opposite side of a star for symmetry. I have two electrons that get excited. They drop down. They emit photons in opposite directions, conservation of energy. There's a recoil impact, conservation of momentum. The recoils cancel out, and we end up with two photons going in opposite directions at the speed of light. Viewed from the right, the photon on the left escapes permanently, can't be found. The blue photon on the right can't catch up to the green photon on the left. This creates an asymmetry in what can be known and where it can be known. The green photon could hit a dust particle, which will eventually appear in the blue photon's past light cone, or the green photon could redshift other photons, so there could be some amount of an echo. So I'll give you a refresher on Minkowski spacetime. We have an event E, and the time moves to the right. We have past light cone in the past on the left, and a future light cone on the right. I'm going to highlight the past light cone shading. Event E can be affected by events in its past. It cannot be affected by events in its future. If you have an oncoming photon. Here, it can't know anything about event E, and event E can't know anything about the oncoming photon either. This photon will have its own sense of the universe. It may know about all the energy in the universe, all the gravity around it. It may have known about the progenitor energy that caused the oncoming photon to be emitted, but it cannot know about the energy in the approaching photon itself. The photon will be surprised to suddenly find additional energy in its rear view mirror, in other words, its past light cone. So we have two photons approaching each other. What can these photons know? They can't know about each other. And just before passing, I'm going to switch to past light cones. And now we continue. As they pass, the photons, the past light cones can overlap, and the events inside the overlapping past light cones can now affect each other. There'll be an exchange of gravitational potential energy. Energy in both photons gravitationally redshift each other. There's no mechanism in this process for chromatic distortion. We have two photon fronts approaching each other. Unexpected energy suddenly appears in each other's past, which only affects the curvature of space-time between them. Redshift looks the same in all directions. If I'm standing on Earth, photons coming in from the left will be redshifted by innumerable photons from the right. Photons coming in from the right will be redshifted by innumerable photons from the left, and no matter what direction I look, the same mechanism exists. So what about the cosmic microwave background? The CMB is asserted to be the remnant of the Big Bang, therefore proving expansion. However, the 2.7K monopole of the CMB has never been measured away from Earth. The Planck satellite didn't measure the 2.7K black body, which has incredible signal to noise. WMAP was only designed to look at differences, not the monopole. The COBE satellite was shielded from Earth's thermal radiation, but it was not protected from microwave radiation from the sides, in other words, from the Earth's limb. In the Earth sensing satellites use the CMB as a reference, but they don't get the CMB from deep space. The 2.7K CMB reference is obtained from the limb of the Earth. It suggests local excitation of the atmospheric molecules are the source of the microwave emissions. Blackbody spectrum is best produced by a vibrational lattice of atoms in molecules. A cooling 3000K plasma of 76% hydrogen, 24% helium would produce distinct line emissions, not a blackbody. A couple of possible validation experiments. A laser emits a pulse of countervailing photons that could create a detectable redshift. If you have a very large telescope array with using interferometry and you eject the laser pulse, it may create a blip that would be noticeable and detectable. Another possible validation is assuming that the photons from a supernova gamma ray burst would create powerful flow of countervailing photons. Photons from more distant galaxies would then be redshifted. If the redshift of the more distant star was recorded before the event, a post-supernova observation may show it to be slightly more redshifted. So here, if you're on Earth and you're looking at a galaxy A on the right, with an unremarkable star E in the middle, if it goes supernova, it'll create high-energy photon front going towards galaxy A, and they could be redshifted. Such a mechanism could possibly explain Halton-Arp's blue-shifted objects near red-shifted galaxies. In other words, some areas got redshifted more than others. Thank you very much. I'll take your questions.